Good afternoon. Section 6.1, areas between curves. So I start with a picture. Okay. Let's suppose that I have two functions. Let's suppose that f and g are continuous functions. And f is greater or equal than g for all x in a certain interval. Okay. So I have an interval from A to B, and this is the curve y equals f of x. And this here, for instance, the curve y equals g of x. Okay? And as you can see graphically, f is greater or equal than g. Okay. Then the area bounded by the curves f of x and g of x and lines x equals A, x equals B. So we want to calculate the area bounded by the two curves on the top and at the bottom, and between the two vertical lines, x equals A and x equals B. So it's this region. Okay. This area, and I continue here, is given by the integral between A and B, f of x minus g of x dx. Okay. So this is just a formula, but how do we really do it? Remember when we started this class, we talked about areas of curvilinear shapes. And then we did something quite lame. We said, okay, our curvilinear shape is this. It only has one curvilinear side and two straight sides, right? So that was our first example of a shape whose area we calculated. And so, since then, we've been calculating shapes of areas of all sorts, but only one side is curvilinear. Here, we have two sides. This side is not straight, and this side is not straight, right? So it's an improvement. It's a generalization of the previous case, and it's a very easy generalization. So how do we figure out the area of this object? From the first principles, like before, we're going to think of it as a carpet. Okay, I'm going to cut it into vertical stripes like this. So let's, for instance, consider this stripe. The base is delta x, just like always. Okay. What about the height? So I go from here to here. So basically, the height of this rectangle is the distance between f of x and g of x. And because I know that f is always greater than g, then the distance is simply the difference between the two, right? So we can say that the area can be approximated as the sum from 1 to n f of xi star minus g of xi star times delta x. So this is height, and this is base of little rectangles. Okay? And then I say the area can be defined as the limit as n goes to infinity of this Riemann sum. Okay? And then we use the definition of a definite integral. This Riemann sum in the limit is nothing but the integral. It's just a different notation for the same thing. And here for the integrand, we take this whole thing, f minus g. So that gives me a way to calculate the area between two functions, also bounded by x values at a and b. Questions? Okay. To explain this definition a little bit further, let's suppose that f and g are positive. Then we have a simpler description. So this is f, this is g, two positive functions. Okay, so, and we have the area by my theorem. The area is an integral between a and b of f minus g, right? So this is what I just wrote. I'm going to rewrite it like this by using the rules of integrals. F of x minus g of x. And consider each of them separately. So what's the first one? The first term on the right-hand side is the area under this curve. Okay. The second term is the area under the lower curve. I'm going to denote it by this. And I take the difference. So I take a carpet of this size and subtract this. And of course, what I have left is the remainder, right? The carpet confined between these two boundaries. And this is A. So when everything is positive, this definition makes perfect sense when I split it into two parts and view each of them as the area. Just the area under the curve. Questions? So examples. The first example is quite easy. So find the area between the following curves. Y equals x squared plus 2 and y equals minus x minus 1 with A 0 and B 1. Okay, so let's draw it to have a visual representation. The first curve is a parabola, x squared plus 2. So it's a parabola that goes like this. So this is y equals x squared plus 2. And the second one is minus x minus 1. So it's a straight line. It's negative everywhere. It has a negative slope, and it starts at minus 1. So like this. And I go from 0 to 1. So it's this. This is the region whose area I'm calculating. And in this case, we simply apply the formula. So the area is the integral from 0 to 1. These two numbers are simply defined by the problem itself. It specifies A and B, right? So these are my regions of integration. And I go y top minus y bottom, right? All I need to figure out is which curve is on top and which one is on the bottom. Which one is bigger? In this case, it's completely easy because, as you can see, this curve is completely positive. for all values of x. And this one is negative if x is positive. And I only need x between 0 and 1. So these are all positive numbers. These are negative. So obviously this one is the one on top. This one is the one at the bottom. I subtract the smaller one from the bigger one. If I confuse them, what do I get? Something negative. And then I'll know, OK, this cannot be the area under the curve, between the curves, right? So if my answer is negative, then I got the two confused. So in this case, it's easy. X squared plus 2 minus x minus 1 dx. So let me rewrite it for convenience. X squared minus 2 plus x. So plus 1, I go plus 3 to save a step. Also, so I have 1/3 plus 3 plus 1/2. You simplify it, OK? So in general, in this case, I know exactly which one's on top, which one's at the bottom. If I don't know, how can I tell? Well, the easiest way is to evaluate this. For instance, I can say at 0, right? This one is equal to 2. This one is equal to minus 1. So I know where they start at least. So just play with the values and see what you find. Another example, which involves transcendental functions. And it's a useful exercise. But conceptually, again, it's very easy. So curves y equals e to the minus x, and y equals minus x squared. And A, again, is 0, and B is equal to 1. Again, calculate the area between these two curves. And I can see that I have a similar argument here. The first curve is the exponent. It's always positive. So even if I don't know how to draw it, I know it's a positive thing. The second one, you can see that it's a negative parabola. So this is e to the minus x. This is x minus x squared. So they never intersect, and one is always bigger than the other. Question?
Yeah. Isn't one thing you could do, write it either which way, as long as you remember it's the absolute value that you get that is returned to you, that is the area between the two?
Yes.
Okay.
Yes. And we'll have more sophisticated examples later. So here, 0, 1, this is the graphics, and the area is an integral from 0 to 1, y top minus y bottom, e to the minus x minus x squared, e to the minus x plus x squared. So what's the, now we have to think a little bit, because let me, here on the side, calculate the antiderivative of e to the minus x. What is the antiderivative of e to the minus x? What's the rule to do this? Let's suppose you don't know the answer, OK? How would I approach this? Substitution, because minus x appears in the expression for the exponent. So du is minus dx. So this is e to u du. So it's e to the u minus e to the minus x. OK? So I can plus c. But I don't need plus c. I have a definite integral here. So I can just say this is the antiderivative is e to the minus x plus x cubed over 3 from 0 to 1 minus e to the minus 1 plus 1/3 plus from the bottom limit of integration, I have a contribution e to 0. What's that equal to? 1. So this is the answer. Okay. Very simple. But it gets a little bit more sophisticated here because curves sometimes intersect, right? So the first example comes from a slightly different formulation of the very problem, which takes advantage of the curves intersecting. So calculate the area of the region enclosed by curves y equals 3x squared and y 2x squared plus 2x. Okay. So enclosed means that somehow when I draw them, I will see what they mean, right? I'll have some enclosed region. For that, the curves must intersect at least twice. So let's draw the picture here. So the first one is a parabola. So this is y equals 3x squared. The second one is also a parabola. I'm going to rewrite it like this: 2x, x plus 1. So this parabola, you can see immediately where it crosses 0 at 2 points, 0 and minus 1. So this parabola is going to go through 0 like this, and through minus 1. Okay, so something like this. But I don't really know how to draw them. Okay, here, what happens? So I need to know whether or not these curves intersect, and if they do, where do they intersect? So question, do these? I already actually figured out that they intersect at 0. That's easy. But let's just ask the general question. Do these curves intersect? Intersect. And this is a question that we'll be asking over and over, okay, when we are dealing with problems like this. How do you find points of intersections of two curves? It's very easy. You equate the first one and the second one. And you have to find all the values of x for which the two functions are equal, right? These are the points of intersections. Values of x for which this function equals to this function. By definition, these are points of intersection. So we end up with an equation like this, which we can simplify. Or we can say x minus 2 equals 0, right? And that gives me two solutions. X equals 0 and x equals 2. I already figured out that they do intersect at 0. And it turns out there's another point of intersection of the two curves. Makes it hard to draw, but I will draw it. 1 second. Sorry, let me just do it better. So now the two curves are different color, at least. Okay. They intersect at 0. And at point x equals 2. And as you can see, there are no other points of intersection. And that leaves me with exactly one enclosed region, which is between these two curves. So I have to calculate the area of this little region, the area of the region enclosed by these two curves. This is it. So how do I do this? In the same way, except a and b are not given. I have to figure out where do I start integrating and where do I finish. And that's given by the points of intersection. I have to start here and integrate up to here, right? So the area is integration from 0 to 2. And then I have to put y top minus y bottom dx. Okay. Again, which one's on top? You can determine by checking the values. Or here, you know that the green curve is 3x squared, and that's the one on the bottom. So I have 2x squared plus 2x minus 3x squared. Questions so far? Okay. From here onwards, it's very easy. The main step here is to formulate the problem, right? The main step is to find the points of intersection, figure out the region of integration, and figure out which one is on top and which one is at the bottom. So now I have minus x squared plus 2x dx. So I got 4/3. If you get a negative answer, then either you made a mistake when you evaluated the integral, or you confused the two curves. So check your calculations. Questions? Okay, so the next is an application. Which I call car chase. Okay. So let's start with a table of values of velocities of two cars, car A and car B, measured at, say, these moments of time. So time is measured in seconds. Oh, sorry, I don't want to confuse it with secant. Seconds. And velocity is measured in feet per second. So let's write down some values. Start from 0 velocity. And then I have these made-up numbers. Okay. So also feet per second. So tell me, which car goes faster? A. Car A is winning, right? So they start with the same velocity, assuming they start with the same at the same point, and it goes faster consistently. Okay. I can even draw these things on a graph. That's a different way to represent these functions. So let's suppose I have 20, 40, 60, and 0, 20, 30, and I have 45, 50, and I have 55, 60. And this was 60, 70. So if I were to connect these, the curves look something like this. So on this graph, the information is available for all values of time. So I know the velocity for each instantaneous value of t. Here I only have discrete values. Tabulate at 0, 2, 4, 6, and 8 seconds. Okay, so this one has more information. This has less information in the sense. Okay, and I want to know what is the meaning of the area between these two curves and t between 0 and 8. What is the meaning of the area between curves VA and VB? So this is VA, this is VB, between t equals 0 and t equals 8. What is the meaning? Okay, let's figure that out. For example, we can calculate this area because I don't have functional forms here. I don't know what function it is. I don't have a picture. I'm going to approximate this by using these discrete values, by using a Riemann sum. Okay, so the area between curves is approximately equal to so I have to take this value minus this value times delta t plus this value minus this value delta t and so on, right? So first one is 30 minus 20 times 2. 2 is delta t. Plus 50 minus 45 times 2. Again, that's delta t. Plus 60 minus 55 plus 70 minus 60. Simplify this. So I have 2 times 10 plus 5 plus 5 plus 10. What's that equal to? 30 times 2, 60. And the dimensionality here is feet per second. So this is feet per second. And this is second. So 60 feet. So I went through the motions, right? I calculated, I approximated the area between these two curves by using a Riemann sum with n equals 4, okay? But I don't know what it means. Let's think about the meaning of this calculation. So at time 2 seconds, okay, I trace the motion of the two cars. This one was going, it's an approximation, so I have the value of 30 feet per second for the first car and 20 feet per second for the second car. We are pretending that they were traveling with this constant speed for the entire duration of the 2 seconds. So the first car traveled, how much? It traveled at speed 30 feet per second for 2 seconds, 60 feet. This car traveled at the velocity of 20 feet per second for 2 seconds. So that's 40. So distance traveled by car A in the first 2 seconds equals 30 times 2 is 60 feet. And car B here is 40 times 2 is, 20 times 2 is 40 feet. So when I subtract one from the other, like here, I actually find the distance between the two cars after 2 seconds, right? 60 minus 40 is the distance between cars A and B after 2 seconds. Okay? So this is the distance between them after 2 seconds. When I keep doing this, all I'm doing is calculating the distance between 2 cars after 4 seconds, 6, and 8 seconds. So the meaning of this area is actually the distance between 2 chasing cars that start their motion at time t equals 0 and at t equals 8. So this is the distance between cars, between the 2 cars after 8 seconds of car chase. Okay, questions? Okay, so when interpreted in terms of velocities as a function of time, this integration, this area between curves, actually tells me the relative distance between the 2 moving objects. Question?
Why is the area expressed as feet and not feet squared?
Oh, because in this case, that's a very good question. In this case, the area has the meaning of distance. So it would only be expressed in terms of feet squared if this axis was in terms of feet and this axis was in terms of feet. Then we'll talk about feet here and feet there. Now these things, this is expressed in seconds and this is expressed in feet per second. So the unit of the area is this unit times this unit. Second times feet per second, so it's feet. Very confusing. Okay, so now we'll go on to look at some tricky problems. So here's the problem. Find the area between curves y equals sine x and y equals minus cosine x and x equals 0 and x equals pi. Okay. Why is this more tricky? For the following reason. So let me remind you about sine and cosine and what they look like. We will need this. So what does sine look like? 0 pi. This is sine x. Now cosine looks like this. So this is cosine x, this is pi, right? Just for your reference. Now my functions are sine and negative cosine. So negative cosine goes through these points. So this is sine x, this is negative cosine x. And I have to evaluate the area between x equals 0 and pi. So what kind of object do I have? So from here to here and between the 2 curves, as you can see, they intersect. So it's actually this and this. So this is my object now. How do I calculate this area? I have to figure out this point. I have to figure out the point of intersection. Do you know what this point is? when is sine x equal to minus cosine x? So you're absolutely right. So sine x equals cosine x at x equals pi over 4. But if I include sine x is minus cosine x, that point gets shifted. And you can see that this is not pi over 4. This is pi over 2. Okay? And this is between these two. So it's 3 pi over 4. Right? The difference is between the difference is that I have minus cosine x. So the intersection point is 3 pi over 4. Questions? So I somehow have to use this information. And what I'm going to do, I'm going to calculate the area of these two objects separately. Okay? So the area is going to be equal to two integrals. One goes from 0 to 3 pi over 4. And it says y top minus y bottom plus 3 pi over 4 to pi, again y top minus y bottom. Except they switch, right? So I have to figure out which one is which in each of these terms. And we can see that from the picture. For the first region, the sign is on top. So I go sine x minus negative cosine x. And for the second integral, I have negative cosine minus sine x dx. Okay? The difference between the two is the sign. Question? No. Okay. So let me continue here. So I have sine x plus cos x dx minus cos x minus sine x. And from here on, it's easy. I have to figure out the antiderivatives and then evaluate the limits. So what is the antiderivative of sine x? Negative cosine. Very good. So the most important thing from now is to not get confused with the sign. So that's negative. And the antiderivative of cosine is sine x. Okay? And that is evaluated between 0 and 3 pi over 4. And I have plus. Now, the antiderivative of minus cosine is minus sine x. Antiderivative of minus cosine is minus sinus cosine x from 3 pi over 4 to pi. So what I need to know is the sine and cosine of 3 pi over 4. It's this one. Yeah. So sine of 3 pi over 4 is minus 1 over square root of 2. Okay, that's a table value. The rest are easy. So to save time, I went through the calculations quickly. You can check at home. You have to remember the sine and cosine of 0. Sine is 0, cosine is 1, right? And at pi, the sine is 0 and cosine is minus 1. What is the main lesson from this? Is that we have to look at the curves and see if they intersect inside the region of interest. Of course, these two functions, how many times do they intersect? An infinite number of times. They keep intersecting, right? But we don't care. We only care about this one particular intersection because we are restricted by the region between 0 and pi. And that's where we have to calculate points of intersection. Now I write down the general formula. Someone already told me the general formula, and it follows from this example. The previous formula we used, remember when we wrote down the definition of the area under the curve, it assumed that one function is always greater than the other. In the last example, it was not the case. So we have a more general formula. More general formula. The area between curves y is f of x, y is g of x, x equals a, and x equals b, is given by the following. An integral from a to b, the absolute value of f of x minus g of x dx. When f was always greater than g, we did not have the absolute value. Now we allow them to intersect and switch, right? Sometimes one is bigger, sometimes the other is bigger. And what we did here, we calculated the absolute value. So over here, sine is bigger. Over here, minus cosine is bigger. To implement that formula, we have to do exactly this. We calculate whether they intersect in the region of interest, and then do them separately. Okay? Otherwise, you will make a mistake, and the answer will contain an error. Fine. So the last example is not dealing with functions, but with a more general object. And let me show you. So calculate area between curves. So the first curve is y squared equals x. And y equals x minus 2. So look at this. Okay? This is not a function. Because if you solve for y, you get two answers, right? So y is equal to square root of x, and y is negative square root of x. So to draw this, we have to look at positive square root of x and negative square root of x. So this curve actually has two branches, a positive one and a negative one. This one is easy. It's a straight line. It's a straight line. And it has a positive slope and goes to minus 2 here, goes something like this. So from this graph, you kind of see that they intersect and they form a finite object, right? Finite region. What do we need to do? We have to, first of all, figure out where do they intersect, okay? Find the intersections. And to do this, we equate the two, and we can do it in terms of y. Y squared is, so we can rewrite this as y plus 2 equals x, okay? So we do it in terms of y. Because these are all the values of y for each, for which x is the same. That gives me a quadratic equation. Y squared minus y minus 2 equals 0. So y is given by your regular formula, 1 plus 8 So it's 3. 1 plus 3 over 2 is 2. And the other one is minus 1. So the two curves intersect when y is equal to minus 1, that's this point, and when y is equal to 2, that's this point. How about, that's 2. How about the value of x? So points of intersection. I want to list them as x value, y and y value. So when the y value is equal to 2, what is the corresponding value of x? How do we determine this? So when y is equal to 2, you can insert it into this formula, and you can see that x is equal to, so when y is 2, what is x? 4. Is 4, right? Why did I choose this formula and not that one? Let's try this one. Y equals 2, what's x? 4. And they are going to be exactly the same. Why? Because that's how we obtained exactly these points. These are the points where the two curves coincide, right? So it doesn't matter which one I use to determine the x value. So when y is equal to 2, x is equal to 4. When y is equal to negative 1, x is equal to 1. Check here, y is negative 1, x is equal to 1. You can see that both formulas give you exactly the same value. So my points become 4, 2, and, I meant to say x equals 1, and 1 minus 1. So mark them here. This is 4, 2, and this point is 1 minus 1. So now, the crucial step. How do I find the area? I can use my previous formulas, but I will have the following calculation to perform. So I would have to split this region into two. In the first region, my top function is y equals square root of x. Can you see this? And the bottom function is y equals negative square root of x. After this point, my top function remains the same, but the bottom function becomes the linear one, this one. And this is slightly tedious, because for this particular problem, I can do better. I can do it all in one integral. And the trick is to not integrate in terms of x, but integrate in terms of y. So integrating in terms of y means that I'm calculating my area by splitting it into horizontal rectangles. Okay? So does this make sense? Instead of splitting it like this, I'm going to slice it in the horizontal direction. So my variable of integration is now y. And the heights are given by the values of x. The right minus the left one. The right one minus the left one. To see that, you have to lie on your side. Okay? Let's do that. Everybody's tired. Lie on the side. And you see the same picture, but x and y are reversed. Okay? So I'm going to perform the integration in terms of y. So the area is an integral of x right minus x left dy. What are the limits of integration? In y, I go from minus 1 to 2. You can see it from this graph. And for the entire length of integration, the function on the right is the straight line, this one. And the function on the left is the parabola. So the integration, limits of integration are from minus 1 to 2. And now I have to write down the functions. So the one on the right is y plus 2. Okay? And the one on the left is y squared. So this is a straight line. and this is y squared equals x. I can call it a parabola, but it's a parabola that is lying on its side. Okay? And from now on, I have a definite integral expressed in terms of a silent variable y. I don't care if it's y or x, I just evaluate it. So I have y squared over 2 plus 2y minus y cubed over 3 between 0 and 2. Oh, I'm sorry, between minus 1 and 2. So I have 2 plus 2 minus 8 thirds minus 1/2 minus 2 plus 1/3. Okay. 6 minus 1/2. Okay, so this is the area. I do this quickly, you can check it at home. Let me reiterate, why is it that here I prefer to confuse myself and do everything in terms of y? Let's again think what I would have to do it in terms of x. I would have to have two regions. In the first region, the top function is y equals x, square root of x. And the bottom function is y equals negative square root of x. In the second region, this remains the same, and here I have y equals x minus 2. So I would have to evaluate two integrals. And I think it's better to do it the other way, because it's only one integral. Thank you.